Now let's see summary of the Laplace transform. So we started out with Laplace transform as a solution for the cases where Fourier transforms do not exist because the signals are not absolutely integrable. So we would make these signals absolutely integrable by multiplying it with an e power sigma t, which makes the signal decay in time and hence make it absolutely integrable. So this is the expression that we have for the forward Laplace transform, and this is the inverse Laplace transform. And we also saw cases where the Laplace transform of a particular signal might be the same as the Laplace transform of a different signal, but they'll differ only in their ROCs. So it can so happen that Laplace transforms expressions can be similar, but their ROCs will be different, and hence a full definition of the Laplace transform could be given by both this expression and the ROC together. The ROC gives us the region of the set of values of S for which the Laplace transform exists. In other words, the Fourier transform of this signal exists. And the most important application of Laplace transform that we saw was that it converts any set of differential equations to simply polynomials in S. And you can solve for these polynomials in S and then find out the solution of the differential equation by taking the inverse Laplace transform. Now, let's look into the properties of ROC. So ROCs we saw that has only parallel strips to the j omega axis or the vertical axis in the complex S plane, and the origin, if that is included in the ROC, it means that the Fourier transform exists. Okay, and this also means that if this corresponds to a system's impulse response, the system will be stable if the origin is part of the ROC of the transfer function. And if the signal is right-sided, then the ROC is also right-sided. If the signal is left-sided, the ROC is also left-sided. And for a finite length signal, the ROC is always the entire S plane because it is always absolutely integrable. And there should be no poles inside the ROC. So when we talk about poles, we have to talk about rational Laplace transform. So the moment the Laplace transforms are rational, you can write such Laplace transforms as some numerator polynomial divided by denominator polynomial. The roots of the numerator is what we call as the zeros, and the roots of the denominator is what we call as the poles. And at the zeros, the magnitude of the transfer function is 0, and at the poles, the magnitude of the transfer function is infinity. So if a signal is right-sided, then the ROC is the right of the rightmost pole. If the signal is left-sided, then the ROC is the left of the leftmost pole. And if it is two-sided, then the ROC is actually a strip, a parallel strip which is parallel to the j omega axis between two poles. Okay, so this is what we saw in our lectures. Now, how do we define the frequency response of a system? Just by looking at the pole zero plot. So around the poles we always have a pass band, and around the zeros we always have a stop band. So if we have lot of poles in one point, then we say that in the frequency range that is around these poles, it is always a pass band. It's going to allow the frequencies in this region, and it's going to block the frequencies which are away from these poles. And if there are zeros here, so if there is only 1 0 and 3 pole, of course these poles are going to compensate for it. If let's say there is a 0 here, then we have a stop band around the 0. So which means here the frequencies are allowed, it is a pass band, and the frequencies are stopped here. So if we have a bunch of zeros, then the frequencies which are closer to the zeros will stop the frequencies which are around them. So this is a very nice concept that we can keep in mind, so that just by looking at the pole zero plot, we can predict what would be the frequency response of the system. Poles correspond to pass band, zeros correspond to stop band. Just keep that in mind. And how do you draw the Bode plot, which actually represents the frequency response of the system? So as long as you are away from the poles and zeros on the left hand side, that is for frequencies which are lesser than the poles and zeros, you can completely ignore their effect, they do not contribute to it. And at the point, from the point of a pole or a zero, you can say that there is a minus 20 dB per decade if it is a pole, or a plus 20 dB per decade if it is a zero. And that is enough to draw the Bode plot. And here we have a table which talks about the properties of the Laplace transform. So if you take the conjugate in the time domain, then you get the conjugation in the S domain, both of the signal and of the value of S. and time reversal results in the flipping in the Laplace domain, and the linearity also is retained, only that the ROC now changes because of the linearity. There is a addition of poles, but zeros are different now. The zeros would be different when you just add two different signals. And time shifts effect is very similar to what happens in the Fourier transform case, same as what happens in the case of uh, S domain shifting as well. And once again, time scaling will compress the signal and will also compress the ROC as well. So it can compress or expand the ROC, and it will scale the poles in zeros. Now, how are Laplace transforms useful in analyzing LTI systems? The nice thing is the complex exponentials are still eigenfunctions of LTI systems. That property carries over from Fourier transform to Laplace transform as well. So it's nice that the convolution time domain, because of that, still continues to be product in the Laplace domain. The thing is that e power st, when s is not purely imaginary, then the signal is not orthogonal anymore, because of which there is no Parseval's theorem, there is no decomposition like the case of vectors. So we do not have Parseval's theorem true for Laplace transform, and the convolution results in just product in the Laplace transform, because of which the ROC changes, poles get simply included, and the zeros are also now included. So now we have a notion of transfer function. The transfer function is nothing but the ratio of the output's Laplace transform to the Laplace transform of the input. Now from this transfer function, we can also comment about the causality and the stability of the system. So if the system is causal, then the transfer function will have a right-sided ROC, but of course the converse is true only for rational transfer functions. And if the system is causal and the transfer function is rational, then the system is stable if and only if all the poles are on the left half of the S-plane. So this leads to the discussion about other set of LTI systems, namely the differentiation and integration operation. So derivative in the time domain leads to the multiplication with S in the S domain or the Laplace domain, and integration in time domain leads to division by S in the Laplace domain. And correspondingly, if you take the derivative in the S domain, we have multiplication by minus t, but we do not have a similar relationship for integration in the S domain here, simply because convolution in the S domain is not multiplication in the time domain for the Laplace transform case. And we can solve a lot of circuit problems by just remembering this one formula. And to understand what happens in the beginning of the circuit and at the end of the circuit, when you turn on the switch, turn off the switch, what is the state of the system? If you want to analyze that, at the moment you turn on the switch, you want to know what happens to the initial value. You can use this expression. At the moment you turn off the switch, and then after a long time you want to see what is the state of this circuit, you can use the final value theorem. So these help us in analyzing circuits, and these equations will help us analyze circuits and design them also. This concludes our discussion about Laplace transform and the course on signal systems. I hope you enjoyed the course, you learned something from this course, and probably will use it for the rest of your degree program, where in many courses you will use the Laplace transform, Fourier transforms, and the concepts of signals and systems to analyze and design systems. If you have any feedback, any comments, please feel free to email me and let me know. And if there are any errors in the lectures or the slides, please do let me know.